Welcome everybody to the third and I guess final of the series of the College of Engineering Dean's Lectures for this year. My name is Greg Miller. I'm the Vice Dean of the College of Engineering, although for the last 8 years or so I was Chair of Civil and Environmental Engineering. And so some of you may have seen me or some of my colleagues before. We're glad you're here. I almost wasn't here because I suffer a little bit from absent-minded professor syndrome, but I'm here. Nowadays you can blame your phone, right? My phone messed up, but this thing messed up tonight. So it's my great pleasure tonight. Our presentation is going to be by Lillian Ratliff. And to sort of provide a little bit of context, those of us who have a spouse or partner, you may play the game that my wife and I play, which is if we're driving around looking for a parking place, she goes, there's one, there's one, there's one. And I, of course, refuse to park at any one that she points out because she always points at it after I've gone by it. So now if you multiply that by all the people that are looking for parking places at any point, whether it's a parking lot or downtown, you can imagine the side effects that has both on, well, marital stress, but also just on the general congestion and movement of traffic in a city. And so one of the cool things that's going on in transportation in general, and again, I know a little bit about this from my home department, but is just the general way in which the use of data, learning systems, and sort of a symbiosis, if you will, between sort of our devices and our own understanding what's going on provides all kinds of new ways that we can do stuff. And so we're going to hear tonight from, again, Lillian Ratliff, who's an electrical engineer and studies game theory, or I should say applies game theory, statistics, statistical learning, coupled with the kinds of data and collection that we can do now to try and figure out better ways to avoid park there, I don't want to park there, and replace it with the idea of, hey, we already know where there's a spot, let's go there, or well, actually, we'll hear more about how it really works, so I won't steal any more of Lillian's thunder. So please join me in welcoming Lillian Ratliff as she talks to us about what it says, improving parking and urban congestion.
All right, thanks for the warm welcome. Yeah, as was introduced, I'm going to talk about making cities smarter for drivers, in particular people here in Seattle, and focus most of my talk on the specific application of parking. So let's start with a little bit of motivation. So I'll talk a little bit about the broad context in which this developing techniques for smarter parking lives. And so that's in this area of smart cities or smart and connected communities. So one of the things that we're seeing quite a bit nowadays is the application or the adoption of sensors and actuators in the cities that we live. So in particular, people own cell phones. You guys probably all own cell phones and use cell phones in your daily life and the decisions you make. But cities also own a variety of sensors, or third-party companies own a variety of sensors to collect data about your daily activities, about the resource consumption that you do. So just to give you a few examples, some of the things that we're seeing are smart traffic lights that can sense when people are at intersections, determine what the queue length is, and then decide what the traffic light timing should be. Another example that I really like, and it's kind of interesting, I don't think we have this here in Seattle yet, but I do think it's coming down the line, and that's this idea of having a trash can that can measure exactly how much waste that you've placed in that trash can and then charge you accordingly based on how much waste you're producing. So just wait, you might have that soon. So now that we have this widespread use of a variety of different sensors and actuators in the environment in which we live, we're seeing this emergence of so-called smart cities. And then with the data that's produced by these sensors and actuators and the kinds of control that we can do, we're seeing a different kind of governance happening, and that's this sort of data-driven governance in which we're seeing this idea of smart cities broaden from just the physical implementation of these different sensor systems to smart and connected communities. So this means involving people in the kinds of governance that we do in a more active and participatory way. Okay, so coupled with sensor deployment and actuator deployment, we're seeing the federal government and our local governments all pushing for this concept of open data. So the idea is that this open data enables, by placing data out in a website or portal or API, as you may have it, this enables transparency, accountability, and civic engagement. So in these open data portals, we're seeing a variety of data sets that span a number of different application areas or a number of different domains in which we have municipal services. So this goes from transportation all the way to public safety. And if you guys have not visited these sites, I definitely encourage you to take a look at the stuff that we have here in the state of Washington and in the city of Seattle. There's actually some cool visualization tools there, so you can go to these sites, you can look at different data sets that are available, and you can then search different data sets and look at, for example, transportation data on a map that they have available within the web portal. Okay, so now that we have sensors and we have data open and available out in the public, what does this mean for the way that cities operate? So what this means, and what I'll keep pointing to in this talk, is that people are evolving from being passive participants, so we are usually viewed as recipients of service, to active participants. So we get to make decisions based on the data that we're seeing. We get to make decisions based on information that's provided to us via cell phones, for example, that we all hold and use in our daily lives. So the sort of biz speak way to refer to this is the so-called digital transformation. And while I'm not usually in the position to be talking about biz speak, so to speak, I will sort of point out what this means, because I do like the picture that it sort of conveys, or the story that it conveys. And so essentially what's going on is that we see first so-called digital competence, and this just means that we're aware of technology, we know what it is. Then we transition to digital literacy or usage, and this just means that we now know how to use different devices in our environment. And the final sort of piece is this so-called digital transformation, which means that now we're integrating these technologies into the way that we make decisions in our everyday life. So let me just sort of dive into that concept within this application of urban mobility. And I'll do it in this abstract setting, and then we'll focus in on a specific application, this application of parking. Okay, so in the abstract setting, the first thing that we have is this, so I'll describe the different layers of this picture and then tell you how this sort of gives us this idea of digital transformation. So the first thing we have is this physical layer. So this means the physical transportation system. These are the roads you drive on. This is the bus routes that you use in everyday decisions, or how you move from point A to point B. I ride the bus every day. I use the 45, which is usually packed with other students and can be kind of a pain to ride from campus to where I live. So that's the physical layer. And then above that, we have sort of the sensor layer, so the sensor actuator layer. So this might be, in this abstract setting, this is where, for example, your cell phone lives, or the smart traffic lights that I described, or smart parking meters, which I'll describe here in the next few slides. And then above that is sort of this cloud layer where we see the aggregation of data. So things are being pumped up from the sensor layer, the sensor actuator layer, into the cloud. And then over this cloud layer, we're seeing the development of new service models and the reformation of old service models. So for example, you might have, I don't know how many of you use One Bus Away. I use that. And this app, for example, is now provided open source, and it depends on data that's provided from GPS sensors that are in the buses that King County Metro runs. And it provides information back to users. They can decide which route to take, and so on and so forth. In addition to services provided by municipalities or our local government, you also have new services emerging. So I'm sure in the last 10 years or 5 years, many of you have probably used Lyft or Uber or something of the sort. And so these guys gather information from the combination of this physical and sensor layer. They decide on how to present options to you, whether that means the price or which drivers to match you to as a rider. They give you a set of options, let's say on your device. You look at these options, you make a decision, and in both cases, whether it be the bus example or this ride-sharing example, you make a decision as a user and you execute it back in this physical layer. So we're seeing this sort of closed-loop process in which the human is now intimately integrated through the access to information and their device into the operation of the physical system. Okay, so what does this mean for us? How can we leverage the data that's available and these new service models to improve the way that cities make decisions about transportation? So specifically, what does this mean about the research questions that someone like myself can address? So I'd like to sort of divide these into 3 categories, which I'll return to in varying stages throughout the rest of the talk. So the first is we'd like to learn plausible models of human behavior and resource consumption with theoretical guarantees based on the smart infrastructure data that we can get from the system. So from this intermediate layer that we're now seeing being placed in between the physical layer and the human decision-making process. The second thing I'd like to talk about is how we can build data-driven policies that promote efficient use of transportation resources. And finally, I'd like to talk about utilizing new technologies to design incentives and information structures that can support the effective use of the data-driven policies designed in this second step. Okay, so away from this abstraction, I may come back to a little bit of abstraction, but I'm going to try to dive into things that we all know about. Like my partner says, it's sticking the hands in the toaster. I don't know what that means, but he says it a lot, so. So let's focus on parking. I'm sure many of you drove here today, and maybe you parked somewhere, maybe you parked on street. How many of you had to park on street here? Yeah. So I don't know what it's like at this hour, but you're probably getting at the point where it could be a little bit tough if there's people coming to have dinner in the area or so on and so forth. All right, so let's talk about this. Why is it a problem? So first of all, cruising for parking. I don't know if you've heard this term, but Donald Shoup, I would argue, is probably the first person to coin this term of cruising for parking. He's a famous parking guy from the University of Los Angeles. And he's done quite a bit of work in this area. So the idea is that cruising for parking causes unwanted congestion, of course. It also causes potentially a decrease in business district vitality. So if there's not parking available, then people can't be patrons to local businesses. It also causes an imposition to residents. If you live in a mixed-use neighborhood, so I'll talk quite a bit about Belltown. Belltown is a highly mixed-use neighborhood, meaning that there's residential, commercial, all of that stuff in one neighborhood. Then people who live there are fighting with people who want to visit there for parking spaces that are available. So this chart that's here, so I don't know how many of you guys read the Seattle Times, but they have this traffic lab section of their newspaper in which recently, I guess in the last 3 or 4 months, they've had a couple articles on parking. And that's because parking is terrible here in Seattle. And this latest, or one of the recent articles, posted some results from an INRIX parking study. And it showed that Seattle, amongst many major cities, Seattle ranks number 5 for worst parking experience. And the 3 criteria that they based this on were search time in terms of minutes per trip. So for on-street parking, which I'll mainly talk about today, not off-street parking, the average search time per trip is roughly 9 minutes. I like this middle one. So this is the annual search time in hours per driver per year. It's 58 hours. That means that the average driver spends more than 2 days plus some time driving around in circles. Can you imagine? That's just such a waste. And then the last one just says, sort of how expensive it is for parking for 2 hours within 1 mile of the city center. So we're not doing too well, being at number 5. I guess we're not as bad as New York, but Seattle's not great. So these things together show that there's a lot of economic loss. There's, loss in terms of human capital in the sense that you're wasting time that you could be using towards productivity in your job or whatever, or in your life. Searching for parking. So how do we address this, and how do cities combat these issues? So one of the main mechanisms by which cities address parking issues is adjusting parking prices. This is not the only mechanism, but it is one that I'll describe in a little bit of detail today. So prices, generally, you might think that that the cities set prices to maximize revenue, but that's in general not their main objective. They really want to balance this idea of minimizing congestion, boosting business district vitality, ensuring residents have access. All of these things are factors in the decision that they make on how to set prices and other policies. So how do they do this? They first, typically, this procedure is adapting over time as more data becomes available. This is historically how it's been done. They establish a target occupancy rate for each block pace between 60 and 80%, and this is applied uniformly, independent of whether or not, what's in the area, who lives there. I mean, it's mostly applied uniformly across a city. They conduct annual studies to manually count parked cars. So I've done this. I did this with my students in the U District area, and I'm telling you this is an arduous process. So this is a little app that we used, and these are some of the blocks in this U District area. Myself and some of my students spent 2 or 3 days walking around, one of which was pouring down rain. I probably walked 30 miles in one day to count and collect information about cars parked. This is not a trivial process, manually counting. So this is done. You get some information about where cars are parked, how many cars are parked along each block face. You get a sample about every hour at this one time that this annual study is done. And then based on where the result of that annual study lies, prices are set based on some prescribed schedule. So this is sort of the abstract, sort of general way in which historically prices have been set. Okay, so one of the things that we're seeing, at least since I think roughly 2011 here in Seattle, is that all these coin-fed meters that you may have had experience with in the past are being replaced with smart meters. In addition, we have phone apps that allow you to pay for parking. And if you don't use the pay by phone parking app, you should. The reason is that you don't have to go to the meter anymore, and you can re-up your, I'm just advertising because it makes my job easier as a data analyst. So please adopt that. But yeah, so you can re-up, without having to go back to the meter. So we're seeing a lot of technologies being integrated into the system. So the question we're sort of asking is, why not use this data in a smarter way, right? How can we use it in a smarter way? Now that we have more data at higher frequency, what can we do? Okay, so why is this a hard problem? You have the data, solve it, right? Just do it. Well, it's not that easy, and there's a couple reasons. The first is that cities only have a couple knobs that they can adjust. It's not like you can just do anything and redesign the entire parking system. Plus, there's a lot of rules and bounds on the policy that you can set. For example, and I may get this wrong, but I think in the city of Seattle, there's a cap around $5 an hour, maybe a little more, a little less, on how much you can charge per hour for on-street parking. So you just can't willy-nilly set the price however you want and then solve the problem, right? So some of the knobs that cities have beyond price are things like the amount of supply that you have. So you can adjust based on how many parking spots that you have along a side of a street. So for example, in certain areas of the city, some parking or on-street parking will be closed for certain hours of the day to allow for peak traffic to flow through. So these are the kinds of things that you can control. Another is this disabled placard holders. So in general, these guys who hold these placards are able to park for indefinite amounts of time and in any place. So some of the things that you could do to control for this uncertainty is to limit the amount of time that they could park for. Okay. So beyond that, cities don't observe what you do as an individual. So I can't track every one of you if I'm going to try to make a decision. I can only observe sort of system-level behavior from the devices that I have in place. And the main devices that the city has in place are these smart parking meters. So I just see paid transactions. Beyond that, humans are fickle, silly creatures, to be honest. Who knows why we make decisions? And it doesn't follow any rational decision-making model, right? And I'll really dive into this in quite a bit of detail later in the talk. There's both, so in the last I don't know, say 5 or 6 years, 2 of the Nobel Prize, Econ Nobel Prize winners have been people who have talked about irrationality of human behavior. So this is a significant factor in the way that we certainly need to consider this in designing policies. Okay, so then the other thing, and this will be sort of the sort of main parts of this talk. So I'll focus on the idea that price, location, and information are key features in the way that we make decisions about where to park. All right, so today's talk in 3 parts. I think I spent too long on the intro, so let's hope that I can get through everything today. So in the first part of the talk, I'll focus on a tiny, small location in a particular city, and I'll say how within this location can we optimize price in order to mitigate congestion that results from people not being able to find parking, from people circling. Then I'll argue that that's not sufficient. I'll argue that that location is a primary driver in where we decide to park. And the way I'll argue this is based on empirical studies. And I'll show that we need to scale up to an entire city and determine which are the locations in which we can set prices according to the model in the first part of the talk. And then in the last talk, I'll really focus on this idea that humans are a major component in the way that the system operates, that we are now operating closed loop because of the way in which that we have access to information, technology, and all of that. And so we'll talk about how we can target information coupled with incentives to make some of the policies that we design in the first step more effective. All right, so let's get started. So setting aside Seattle for a moment, and the only reason we're doing that is because there's this fantastic study that was done in San Francisco, which is sort of, I would argue, our sister city in some sense. They have a lot of similar characteristics to the way that we do, in the sense that they are also impacted by the technology boom and the influx of people, although they've experienced it much earlier than we did. So they've done this amazing study there in San Francisco in which they've been able to adjust prices dynamically and thus get a sense of how people respond to price changes. We don't have this data here in Seattle as of yet, so I'm going to focus on San Francisco for that reason. Okay, so what is the SF Park study? So essentially what they did is that they got some money from the federal government to be able to do this 2-year-long study. It's really well done in the sense that they did both a control group and a test group. Not a lot of studies are well designed in that sense. And what they did is they changed prices and tried to get people to change their parking behavior. So they developed an app. These are screenshots from the app. They picked certain neighborhoods in the city of San Francisco to target this study. I'll be honest, they had a lot of pushback because people didn't want, the general public thought that there may be some issues with adjusting prices because it may cause too much traffic in their neighborhood. So just the imposition that smart meters and technology was having on the San Francisco citizens was sort of rejected, right? So this, again, sort of points to the human behavior element. So they were able to get it to running in a few of the neighborhoods within San Francisco. What they did is they, in their app, they showed availability, so based on colors, so which blocks had parking, and they showed the price as it was changing dynamically. And they varied rates by block, time of day, and day of week. They didn't, if you look here, they're not doing major fluctuations in the price. It's very small, so minor things. They conducted 2 trials. The first, which had little effect, and the primary reason is, again, because nobody knew what was happening. So after they did a targeted ad campaign, suddenly things started happening. People were suddenly aware. So I'm going to come back to this idea towards the end of the talk. The key thing here that we're going to use in this first part of the talk is the data that's available from this study. And so that we know what the price changes are. There's hourly ground truth occupancy. They put in pucks to sense who was parking. They also placed sensors to collect information on traffic volume on key thoroughfares, key arterials. And then we know what the paid transactions were at the smart meters. Okay, so to start, we're going to develop first a reasonable model, what I would argue is a reasonable model of parking behavior along block faces. And we're going to take a data-driven approach or a data-informed approach to learning the parameters of that model. So usually, if you think about a queue, so we're going to model the parking as a queue. So usually a queue, what happens is, for example, you're at the, the airport, you got your passport and your ticket, and you stand in line at security. You wait. There's several guys who are going to check your information. When one of them finishes, then you get served, right? But there's this long line, there's a queue. You can't do that with parking, right? So that's not what happens. What happens is you arrive along this block face. If there's some spot available, then you park, you're in service, and then you exit the network. Otherwise, you get rejected. There's no queuing on the street. You can't do that. So we kind of have this different queue model in which this is a zero-length queue. So we can couple these queues together to model a city. So you might have a block face like this. Each of the block faces represents a queue. Rejections, so you can't park on this block face, let's say. Then you get rejected to a different block face. Depending on the structure of the network, you can turn left or right or so on and so forth. So we can couple these together to get this graph structure. Okay. This is as much math as I have in the whole talk. So right, okay, so the goal here is to take our queue model. We want to learn the parameters of the queue model from the data that we have, and then find prices for parking, so prices for each of the blocks, such that we maximize the utilization, so maximize occupancy, and keep the rejections that occur through as modeled by the queue setup that we have below an upper bound. So the first step is actually to learn from the data that we have the appropriate maps. The first one is the price elasticity. So we want to understand how occupancy, so the behaviors that we're observing from the data, varies as a function of price. The second is we want to learn how this rejection process varies as a function of the price that we set. So this is essentially our data-informed queue model that I described. So once we've done this learning process, then we can formulate an optimization problem, and we can show that this is a computationally feasible optimization problem to solve. So we maximize the occupancy for each of the blocks over the price, and subject to the fact that we don't want rejections to be above some congestion bound. All right, so how do we implement this in practice? So again, I just want to reiterate what the data we have. So we're looking at this mission area of San Francisco. It's a highly mixed-use neighborhood. There's a lot of restaurants down there. There's more and more businesses opening up. So many of the tech companies are now moving into the San Francisco area and opening shop here in the Mission District. So it's a nice example in the sense that it's mixed use. We're going to look at 16 blocks in this area. The data we have is hourly ground truth block level occupancy, smart meter transactions. We know what the price changes were. We also have traffic volume counts on a subset of the roads. And in the example I'll show, we have we're going to consider a typical Saturday afternoon at noon. So there's so one of the things that I totally miss about the Bay Area is the Mexican food. Up here, there's just nothing spicy enough. It's so bland. And there's just tons of good Mexican restaurants like right in here. So I'm sure on Saturday afternoon, that's what people are doing. They're just eating Mexican food in the Mission District. So anyway, in the Mission, at 12 p.m., you have, along all of these blocks, you have an average occupancy of about 78%, for each of the blocks. And over 60 vehicles per hour are generated in additional traffic because of cruising for parking. So our solution is going to be to maximize the occupancy such that along each block, the utilization is above 85%. So we are encouraging a lot of usage while not meeting the maximum bound. So we're not getting it at 100%, but we're making it so that, like, for example, there's at least one parking spot open on average. And we're going to do that subject to some congestion bounds, so that is lower than what we see in the average case. So in particular, we're going to say that only one vehicle every 20 minutes is unable to find parking. So that results in 48 per hour for all 16 blocks in this area. All right, so what are the results? So in the normal parking case, you're looking at a couple different plots here. So in the top part, so first in this right column, what we're looking at is the percent occupancy, where the x-axis is the index of these different block faces. The only two we really care about are these two that are in boxes here, and I'll tell you why in a minute. And the second plot shows you the number of vehicles that are rejected per hour, again, where the x-axis is the index of the block face. So in this top bit, this is the normal scenario, and you see that there's a variety of different average occupancies for these blocks. There's 2 that are really high. And if you look at the number of so the congestion as a result of whatever is going on in the parking system, there's these 2 blocks that I pointed out here are the ones that are the cause of the congestion that we see. So all of the congestion is being generated by those 2 blocks. And it's these 2 that I've highlighted here. So when we optimize things, we can redistribute parking evenly across the neighborhood so that all the blocks are being at a high utilization on average. And the number of rejections that we're seeing per block face is really low. And it's evenly distributed. So we're not getting everything being generated from the same 2 blocks. So you might ask, what did that cost me? Is that going to cost me a lot of money? So am I going to have to pay a lot more money to see this kind of redistribution of utilization? And the answer is no. So this is the prices that we see when we optimize this objective. So most blocks, almost all of them except for the 2 culprits, get a lower price, right? And it's not a significantly lower price. We're not talking about a massive loss in revenue, for example. And those that had to increase didn't increase more than 50 cents per hour. So this is a nice result, right? Well, how does this jive with parking studies? It doesn't. So the key assumption here is that users know what the prices changes are. In general, you don't, right? I mean, these things happen, and then over time, you learn after many days of going to this area, you finally learn maybe what the price is. In addition, we assume that elasticity is uniform across the neighborhood. That's also not true. There's a variety of different elasticities depending on what's in the area, what businesses are there that you're trying to visit, or whether or not you live there, for example. So what type of user you are. So these are key things that are important. So price elasticities vary across the neighborhood. Location is the primary driver of parking choice. Many studies show that this is the case. In one particular study in LA, 50% of people parked within 1 block of their location. So that means they're not willing to adjust based on price. Like, price may not be the reason that you park in a particular area. The other thing is that information is key. Surveys indicate roughly 60% of people don't even know what price they paid. So this is an LA Express Park study. This is sort of a mirror study to the one that I described for San Francisco. And these are online and intercept survey studies that say what is the percentage of people who are aware of different things. And this is the awareness of pricing changes. You see, it's like 20% and 31%. So most people didn't even know it was happening, right? That there was any change. Same thing for time of day, whether or not people knew there was time of day pricing, and whether or not they knew there was a mobile app to help them. So this lack of information is really important. So I'll try quickly to talk about these 2 things. So location as the primary driver of parking. I'll show you how we can divide the city in a smarter way based on the data that we have. And how information is important. So how the human element needs to be integrated into the decision-making process. So now we're going to go back to Seattle. We all care about Seattle. This is where we live. Well, presumably you all live in Seattle. So how are prices set? It's exactly as I described before. Data is collected in yearly manual studies. There's a target occupancy range. And this is sort of a broad generalization. Things are changing now that data is available, but in general, this is what's done. There's a target occupancy range. There's predefined zones. Most of the zones in Seattle are by neighborhood, so it's the neighborhoods you know and love, right? So we know Belltown, we know South Lake Union, we know the Denny Triangle, so on and so forth. Prices are set within those zones. There's a prescribed schedule that says, okay, if your manual study doesn't fall in this range, we're going to do something to change the price. Prices are quasi-static, so there's time of day pricing, but in general, they're fixed for the year and then revised yearly. But we have new data available, so let's try to do something slightly different. And the first thing we're going to do is revise the way that we divide these zones up and do it based on data that comes from observing how people actually consume parking resources. So let's focus on one neighborhood, Belltown. Belltown is the most dense neighborhood in Seattle. It has the highest density of blocks with on-street parking. So you can see most of the blocks, all of these colored blocks have on-street parking here. It's a very highly mixed-use neighborhood. There's all kinds of things going on there, from residential, tourist things, commercial stuff. And the usual, or the way in which prices are set is that we take the Belltown neighborhood, we take this is Bell Street, although you can't see it, and the below Bell Street is one price and above Bell Street is another price. Okay, so we're going to try to take the data that we have available and divide or group the blocks into, partition the blocks into groups that have similar demand characteristics, similar occupancy characteristics. So that's the question we're going to ask. And the approach we're going to use is this so-called Gaussian mixture model, which is a probabilistic model for deciding which groups should, or which blocks should fit together. So how do I partition this set of blocks into a separate or a finite number of groupings? And so if we only cared, this picture is to sort of provide you a little bit of intuition. So if I only cared about occupancy, the way this would work is I would optimize over the number of these blue curves here. So there's 3 in this picture. And I would try to say, okay, given the data that I have, should each block be associated with this group, or this group? But in practice, we don't care just about occupancy. We also care about the location. So I'm going to pass in 3 features, the longitude, latitude, so the location, and the occupancy. And then using paid transactions from 2 years, so the recent 2 years, 2016 to 2017, within each season in the year, we're going to develop a Gaussian mixture model to partition the city for each day of week and each hour. So this allows us to create still simple parking policies that are easy to understand while leveraging the data we have available. All right, so here's the result. So I'm just reminding you of what the current partition looks like here on your right. And this picture on the left is the result of our study. So what are you seeing? So there are a bunch of little dots. All of these dots represent a block face that has on-street parking. These larger red dots represent the centers of the location. So there's 4 colors here. All of the pink ones, for example, or magenta, I think that is, belong together, and so on and so forth with the other groupings. The red dot is the center of these groupings, and these concentric ellipses tell me the spatial variation, like how much it varies within that grouping. I think what's cool, there's a couple things to point out here. One, the optimal number of partitions is 4, it's not 2. 2, we just use this occupancy and the location information, and we get out something that is interpretable in the way that the city already operates. So for example, this magenta region is where there's the highest density of bars and restaurants. This light cyan color is where we have mostly residential stuff going on. This light green area is where there's all the cruise ships coming in, and then there's the sculpture garden. So there's this mix of kind of residential plus tourist attractions. And then up here, we're like on the boundary of where we have the science center and all of that stuff. So this is a very touristy area above that, and so a lot of parking of that sort happens in that area. So this is a natural arising of this partition of Belltown from the data. So we didn't tell it that's what was going on. It just happened that it pulled these things out. Okay. So you might say, okay, well, how does this depend on day, or how does this depend on time? Well, it doesn't actually change that much in time. So I'm just showing you for Friday. Most weekdays are the same. So I'm just showing you for Friday. What happens is that the day is partitioned into 2 time periods, which means that we can still stick to these simplistic policies. The first time period has a Gaussian mixture model that over each hour of the day that's fairly consistent with the picture that you're seeing. So I picked 11 a.m. to show you here. And then it switches at 3 p.m. Something else happens based on the user characteristics, and you get a slightly different partitioning of the city, and it's fairly consistent from 3 to 8 p.m. The other question you might have is whether or not price drives. So you might say, okay, well, price is a conflating factor here, right? Price is the thing that is underlying that you didn't consider in your model that's driving the results, and that's not true. So we can look and see that this top plot is showing that there's actually, so we looked at 2016 to 2017. In the north part of Belltown, there was a difference in price of 50 cents per hour. So 2016 was $1.50 an hour. 2017 it's $1 an hour. And this top plot shows you that there was a lot of fluctuation in the occupancy. So they said the positive and negative changes in occupancy per day, per hour. The point is not exactly what's in the plot, but just to see that there's some change. However, the mixture model itself did not change. The centers are, I mean, there's a little bit of change in the shape of the clusters, but the centers are in the same location. So this, to me, tells me that location is really the primary driver here. So it reaffirms our hypothesis. All right, so how do we use this data? How do we use this model in particular? So first, our conjecture or our suggestion is that cities can rezone based on the new partition that we've prescribed, or that is prescribed by our Gaussian mixture model, or our approach. But that's not, as I pointed out at the beginning of the talk, that's not enough to affect change, right? And the reason is that the first thing that we showed is that price changes are only effective if people know what the price is, if they know what the price change is. And the second thing is that location is the primary driver here. So what we want to do in this last part of the talk is describe to you how you can target information in order to increase price awareness, for example, and couple that with an incentive to instigate change in the way that we consume parking resources. And we're going to do this in locations of similar demand, right? So this Gaussian mixture model allowed me to identify groupings of blocks that have similar characteristics. So that's the last part of the talk, and then I'll conclude. All right, so let me tell you why people are silly in the way that we make decisions. So this is I love this plot, and it's not the way that, so this is a plot of Uber data, and it's not the way they set prices anymore, but it's a great example of how humans react to the view of a loss or a gain, or the perception of a loss or a gain. So what's going on here? Okay, so there's a sold-out concert in New York on some day in March in 2015. And so what happens is that the concert gets out at 10:30 or is getting out around 10:30. And during this period from 10:30 to, say, 12 or 11:45, roughly, there's a surge price in place. And why is there a surge price in place? The reason is that these red dots show a ramp up in users opening the app. So Uber can see when people open the app. So there's a significant ramp up here. And there's not a big enough ramp up in supply of drivers. So Uber can see this. They institute a surge price. And what you see is a significant drop in the number of passengers that are opening the app after that surge price is in place. Whereas you only see a marginal increase in the number of drivers that show up in response to that. So this, to me, says that passengers see this surge price as a major loss. It's a big deal. I don't want to pay that price, right? It might be 4 or 5 times the amount. That happened to me when it snowed here and I was at the airport last year. I hope that doesn't happen this year. It was terrible. It was like 400% price to get home. So yeah, and the drivers just see this as a marginal gain. This is just an everyday activity for them. Sometimes the price goes up, sometimes it goes down. I'm doing my job, right? It's not that big of a deal. So this sort of highlights the difference between how we view gains versus losses. So let me dive into this concept a little bit further. So the way that we make decisions, there's a variety of factors that play a role. The one that I'm going to really hone in on and focus on is the fact that we compare, when we make decisions, we compare things to reference points. In particular, we compare things to the status quo or recent expectations about the future or past experience or just random things. I mean, there's a book. Danny Kahneman is the one who is one of the people who won the Nobel Prize for his work on prospect theory, so in behavioral psychology, economics. And he has a great book called Thinking Fast, Thinking Slow. And if you haven't read it, I encourage you to. It's a nice pop-sci book. And there's some really good examples of how people just pick random things in their mind to compare to, because they just don't have anything else. They just grab onto whatever is available, right? So that's one of the things that we do. In the context of parking, we might, it might be based on, what mood we're in, but more likely it's based on how long it took you to find parking the previous time that you parked. So we might decide whether or not this is a gain or loss in terms of how much time we spent searching for parking by comparing to what we had experienced in a previous instantiation of that experience. In addition, we compare reference points to the change in probability of events. So in the context of parking, I might say, what is my chance of finding parking? If the probability of finding parking goes from impossibility, so 0%, to a slight possibility, the value I place on that in general is much larger than if I saw an incremental chance in my potential to find parking, so 45 to 55%. And the value of going from possibility to certainty is even greater so that's even greater than this, the one here I'm showing on your left-hand side. Okay, so how do we integrate this into our model? So we want to take advantage of the fact that we know people make decisions by comparing to reference points. And we also want to leverage our data-driven approach to identifying locations where people have similar utilization characteristics. So what we're going to do is take the locations that we identified by our Gaussian mixture model approach in the second part of the talk, and we're going to treat these as areas where the demand that we're observing is a proxy for the user behavior. We're going to say people in that area have similar preferences. And so let me describe to you how this concept works. So you're a user, and you're getting ready to park. You're going to leave your house, and you're going to go park somewhere. You might observe the system in some capacity. So this might be through a dynamic message sign. So right now, there isn't dynamic message signs that tell you where to park in Seattle. There are apps that give you suggestions on how likely it is to be able to find parking in certain areas. There are dynamic message signs that say for off-street parking, whether or not parking is available. But hopefully in the future, we'll have a bit more of an advanced system in that regard. So you observe the system in some capacity. You have a reference point that we assume is drawn from a common distribution if you're going to park in a similar location to other users. We offer an incentive, so this might be a discount to a local business that changes your reference point. So I don't care so much about driving in circles if I get free coffee, right? Then I make a decision about where to park, and I execute that in the neighborhood. And then the incentive designer, the person trying to affect your decision, observes the occupancy at an aggregate level. So this is our setup, right? So the reference dependence is factored into the way that we're going to design incentives to change people's behavior. So let me just give you a little bit more of an example scenario. So your reference point in the context parking might be a weighted combination of your search time to find parking and the cost that you pay. And this is unknown a priori to the incentive designer. You may have some prior distribution or belief about what people do, but you don't know exactly what people's reference point is. You design an incentive that is a discount at a local business for parking at designated blocks. You might say, how do I validate that? How to make sure that that's actually happening? Well, we could use, for example, the Pay by Phone app, which is already a mechanism that exists in practice. And we can, with this Pay by Phone app, it'll record which block that you paid at, and then you can use this at the business to say, I'm going to get a discount. And then what do we observe as the incentive designer? We observe the occupancy distribution across the neighborhood. All right, so I'm almost done, just like one or two more slides. So how do you solve these problems in general? How do I determine what is the best incentive to offer given the observables that I have? Observables being the distribution of parking consumption in a particular neighborhood. Well, the usual way these kinds of matching problems or determining what is the best thing to offer is solved through the so-called Multiarmed Bandit approach. And so what that means, or what you can think of, is a series of slot machines, all of which have different intrinsic values, and you're trying to pull arms to figure out which one is going to give you the best reward. So I can think about this problem of designing incentives in the same capacity. I can try to offer an incentive, see the response that people have by observing the occupancy over time, and see whether or not that was the right thing to do. So the question is, how do I do this in an effective way? How do I do this while minimizing the time that I have to spend to explore the incentive space? So just to reiterate, the arms in this case, the things that I'm pulling on the slot machine are going to be different incentives, so they might be different values of discounts at local businesses. The reward that I'm observing is going to be a function of a variety of things, including this unknown a priori user reference point. So I don't know what you guys compare to in your mind, but I have some idea in terms of a probabilistic representation of that. There's going to be some cost for offering the incentive. It's not free, to offer a discount. And there's going to be an effectiveness of that incentive at redistributing the parking. So how do we metrize the performance in this context? So I'm going to try to design an algorithm to explore these different arms. And I want to do so to minimize this concept of regret. It's exactly what it sounds like. Regret is regret, right? It just means what it means, in the sense that we just compare to the thing that would have been the best thing, and then if we didn't meet the best thing, then we have some regret about that, right? We have some disappointment. It's exactly the same thing here. I compare to what, if I pulled the arms for in time instances, and I compare to what would have happened if I knew what the best arm was, so I knew what to offer you guys, I knew what was the best match for you. I just compare that, having done that at every time step, to the reward that would have happened if I had or whatever reward that I get from selecting a particular incentive under my algorithm. So I want to design an algorithm that minimizes this. So I can do that. And I won't go into the details, but I'll just tell you that we can come up with theoretical bounds on this, and then when we do simulations, what we can show is that, of course, our regret decreases. So we eventually find the best arm, essentially. Our average reward increases to the optimal expected arm. Again, we're finding the best arm. And I think that the main interesting thing here is that depending on how long we let the arm run, so this is kind of interesting, right? Because this also gets back to human behavior. So if I let the incentive be in place long enough, then I'm able to observe more of your response to that incentive, and there's no confusion about whether or not that your behavior is from some other exogenous factor. I get more and more certain about the result of that incentive. And so that's what we're seeing with these two different color things. So I'm showing you some different amount of time for allowing the incentive to be run. So this longer one is the orange one, and the shorter one is the blue one. And so the regret decreases more quickly the longer I allow this sort of mixing to occur. So yeah, that's one of the key things. The other thing is that our algorithm, of course, identifies the best incentive. Okay, so that was the theoretical result. How does this translate to practice? The goal is we have this ongoing collaboration with folks at the Seattle Department of Transportation and people in the U District Partnership, which is a business improvement area here in the U District, and a local company, IDAX, as well as funding from NSF to support actually deploying these incentives that I'm describing. So we're going to, in the spring, that's the goal, be able to deploy information coupled with incentive mechanisms to try to change people's behavior in these local areas. Okay, so that's it. I'm just going to wrap up here and say a few things. So I talked about a very specific application in the area of transportation, but I really want to say that there's a lot more going on in this transportation area in terms of designing better policies, whether that be traffic light control policies or, as I described, parking policies. What is important is that there's now streaming data available, open, usually made open through these open data portal initiatives that allow us to move towards smarter governance. It also increases transparency, as I mentioned, so that, and increases civic engagement so that you guys can be aware of what's going on. This concept of the digital transformation, so this idea that we now have humans closed in the loop, allows us to design adaptive policies that are occurring at higher and higher frequencies. So I might not be able to change price very frequently. I can still do it on this yearly basis, make it simple so everybody understands, but I can design these incentives at a much quicker rate, right? If it's not working, toss it, do something else. And I can do that much quicker because we now have ways to communicate with people through the devices that they have in their hands. And I think the key takeaway here is that you can't ignore the human element. It's very important. The way we make decisions really determines the performance of the system. Okay, and I'll just conclude by saying, obviously I did not do all of this work. I would like to really thank the graduate students who have been involved, and I'm really excited to have these three young women who are undergraduate students here at UW to be active in the research. And then, of course, my colleague, Gaussian, who's another professor who works actively with me, and our shared postdoc, Shreyas. And then we work with several people at the Seattle Department of Transportation, without which we would have no idea. I mean, I'm not a domain expert by any means, and without their help, I'd be walking in the dark here. So I really appreciate that. And then people, of course, in local industry and the National Science Foundation for funding this work. So thanks, guys, and please let me know if you have questions.